All right. Good morning, everyone. I'm going to speak about argument text today, argument classification and clustering in a generalized search scenario. My name is Johannes Daxenberger, and I have been leading the argument text project for the last couple of years. The talk is going to give you an introduction to argument mining, which is the research direction behind argument text. And after that, I'm going to dive into the main part of this talk, which is about the argument text project, and will tell you how we applied argument classification and clustering to heterogeneous text data. And then finally, I'm going to conclude with a few research and commercial applications that will hopefully show you how you can apply argument text to your own research or your own applications. Why should you care about argument mining? What is argument mining actually? Well, first of all, it is an advanced content or text analysis method, and it solves some of the drawbacks of the existing content analysis methods for big data, in particular that they mostly rely on superficial properties like lexical cues or simple word counts, and that many of them are actually too complex to be deployed into existing workflows because they assume that you know a lot about the underlying data, about the underlying distributions, and so on. Arguments, natural language arguments carry core information for decision making because they highlight not just the courses of action, so what you could do, but also the advantages and disadvantages of those actions, which obviously speeds up the decision-taking process a lot. The natural language processing research field called argument mining is an increasing discipline that has received quite a lot of attention in the last couple of years. And in that context, argument mining is typically defined as detecting and structuring natural language arguments in textual data. There are two basic directions of the recent research and applications of argument mining. The first one is closed domain discourse level argument mining, which focuses on the argumentative structure of documents. On the other hand, we have the open domain topic dependent argument mining, which is also referred to as argument search. Now, closed domain, what do I mean with that? Closed domain basically means that you can apply this paradigm to documents that stem from a single distribution or a single domain, like, for example, essays or news articles. Whereas open domain basically means that you can apply it to any sort or any collection of textual data that can also be heterogeneous. Typical applications of argument mining are in the education sector, but also in the legal sector or in journalism. And this talk is going to focus on open domain topic dependent argument mining, because this is basically the paradigm that we applied in the argument text project, because we wanted the technology to be able to deal with any sort of text. I'll give a bunch of examples later on. Let's start with discourse level argument mining. This research paradigm mostly uses the so-called claim premise model. Here on the slide, you can see an example for this model. So a sentence like automated essay scoring can be used to reliably assess the writing skills of students because it is based on elaborated NLP technologies that could not be cheated, would be separated into two components. The first one is a claim, the second one a premise, and the premise supports, in that case, the claim. So the premise is basically the evidence. In that case, it is based on elaborated NLP technologies, and this is in support of the claim, which would be that automated essay scoring can be used to reliably assess the writing skills of students. If you use this to structure an entire document, as in this case, a student essay that you can see on the left side, you can actually parse this entire document, resulting in an argumentative structure, in that case a tree that you can see on the right side. And this tree in that case would consist of two major claims, which basically reflect the overall opinion, so to say, of the author of this text. And these claims are then further backed by supporting or attacking claims that basically structure the essay. And these claims are further again attacked or supported by a number of premises that would give evidence for or against the individual claims. How to actually put this into practice? Our goal in all of the research that I'm going to present in this talk is to do this automatically, which means that we want to teach a machine to actually understand the text and automatically process it. In the case of this essay, we want to parse it into a discourse tree. One way to actually make this feasible is to apply sequence tagging. And here is an example on how this could work. So in the example, since it killed many marine lives, tourism has threatened nature, we again have a premise and a claim. And this premise is in support of the claim. So here you would simply tag each individual word in this sentence with a tag that describes the component type, so a claim or a premise. And in addition to that, you also specify the relation type and the distance between the individual components. So the distance in that case is 1, because the claim that is in support of the premise that is in support of the claim is just the 1 position away, so to say. And in addition, you also specify using the BIO scheme where the component begins and where it ends, and all of the tags or the words in that case that are not relevant here. And then this is something that you can use to actually learn a sequence tagging model. For sequence tagging, there are, there's a lot of architectures, a lot of models that you can use, so to say, out of the box to actually learn tagging arbitrary text. And here are some numbers from a few years back in which we applied a sequence tagging scheme to student essays in this case. The first one is a rather simple model based on CRFs and SVMs, which have lexical and semantic features. And with that, that is the Stab and Gurewicz 2017 one in the lower row. That already gives you an accuracy of 60% on this selection of student essays. And we also applied a neural model, in that case by LSTM, which is able to parse long-range dependencies. And in addition to that, this particular architecture also uses a CNN for out-of-vocabulary words and a CRF to model the label sequences. And that gives you an F1 score of up to 75 on components, in this case, major claims, claims, and premises. The 50% means that they have to overlap at least 50% the predicted labels and the ground truth. Okay, now let's turn to topic-dependent argument mining. So argument mining in heterogeneous sources. The problem with discourse-level argument mining is that it relies on argumentative text. So as I've shown on the previous slides, the assumption is that you actually have some sort of an argumentative structure in your text. Otherwise, it is really hard to actually apply such a parsing scheme. So this only works for texts that are argumentative and that kind of follow a consecutive structure in terms of the argument components. Now, as for topic-dependent argument mining, you can extract arguments from any text. This is why I refer to it as open domain. And the basic idea is you have a collection of texts that could come from a web crawl or a newspaper corpus or social media, whatever you can imagine. And the only thing that you actually need is a topic of interest. So that is your query, so to say, your search query. And as a result, you basically want a list of pro and con arguments. A few definitions before I give a couple of examples. In this context, topic-dependent argument mining, an argument would be a span of text expressing evidence or reasoning that can be used to either support or oppose a given topic, and this topic should be some matter of controversy for which there is an obvious polarity to the possible outcomes. So in comparison to discourse level argument mining, the topic would be part of a claim or major claim, and the arguments would be the premises that support or attack the claim or major claim. In that case, topic-dependent argument mining is a very flat model. It doesn't consist of various hierarchical layers, and very important, it only considers arguments in isolation from their surrounding context. So we only look at a single sentence, for example. The goal of topic-dependent argument mining, once again, is from unstructured text in the beginning, you extract spans that express evidence. Spans, as I mentioned, could be isolated sentences or paragraphs of text or a few words. And in the end, you have a summary or a grouping that is basically a list of pro and con arguments. Now, here are the examples for a sentence level classification task that would distinguish between pro arguments, con arguments, and non-arguments. So 3 classes. For the first row, the sentence on nuclear energy. Nuclear fission is the process that is used in nuclear reactors to produce energy using an element called uranium. Now, that is not an argument because it is a mere description of what nuclear fission is in this process. It doesn't contain any reasoning or evidence. The second example, the amount of greenhouse gases have decreased by almost half because of the prevalence in the utilization of nuclear power. Now, that is obviously an argument and it has a positive stance, so it is a pro argument, whereas a 2014 study found that minimum workers are more likely to report poor health and suffer from chronic diseases would be a con argument for the topic minimum wage. And one more example on the topic of minimum wage, we should abolish all federal wage standards and allow states and localities to set their own minimums. Now, that again would not be an argument because it contains an opinion, but not any sort of reasoning. So this is only claiming that we should abolish federal wage standards, but doesn't really give any reasoning on this. So this would be counted as a non-argument. Okay, so far for the research background on argument mining. Now let's go into the actual argument text project. Most of you are using Google, I assume. So if you wanted to look for arguments for or against animal testing, what you could do and what you probably would do is you turn to Google and scroll through a lot of pages and basically manually extract the arguments from those texts. What we want is something like this, which is basically a search engine like Google, but it does retrieve arguments for you directly, so you can enter any search topic that you're interested in, like animal testing in this case, and then you actually get a list of pro and con arguments that have been extracted from the underlying document collection. And more than that, even we want to cluster the resulting arguments, so we don't want the readers to have to go through a lot of similar arguments. So we actually want to group the arguments into clusters that can be labeled and that it is easy to scroll through. This is, we solve this using a number of quite challenging NLP tasks. So the whole pipeline is basically consists of a few individual steps, which I'm going to show in the following. The first one is argument stance detection, which is a sentence classification task that needs to distinguish three classes as shown in the previous examples: pro, con, and non-arguments. It is trained in the sense that we have training data for it. So the machine learning model that we use to actually perform this task is trained on manually labeled data. In the second step, we need to rank the arguments. So the list of pro and con arguments for argument search need to be ordered. And the output of this would be a list of sorted pro and con arguments. This task is not trained, so it is determined from the output of the first step. In the third step, we then cluster the arguments. In terms of the task, this is a sentence pair similarity task. So we determine the similarity of a pair of sentences, and then from that we calculate the clustering. This again is supervised, so to say, trained on manually labeled data, not the clustering task itself. That is unsupervised, obviously, but the similarity function that determines the distance between two sentences or two arguments, that is actually supervised. So we have training data for that. And the output of this would be groups of similar pro and con arguments. And then finally, we also label the groups of arguments, and we use a task called aspect detection for that. This task is a sequence labeling task because we want to extract meaningful sequences, so meaningful words or engrams from the arguments, and these sequences are used to label a group of arguments in the end so that you don't have to read through all of the arguments. This again is a supervised task because we have training data for it. Okay, now in the following, I'm going to show you examples and also explain a little bit on how we actually created the data for all of these tasks. And I should also mention that for all of these steps, our methods are able to perform this on both German and English data, and in some cases also for a few other languages. Okay, let's start with argument stance detection and ranking. The data generation process for this was as follows. We extracted document collections from a web search, so to say from a large web crawl. And the topics that we have been looking for documents in the first place span by now more than 100 topics. The task that had to be performed manually to create this training data was given a controversial topic. So this topic was given label a text, in that case a sentence, as pro or con argument with regard to the given topic. And this manual labeling was performed using crowdsourcing. So we basically put our data on the Amazon Mechanical Turk platform, where a lot of people then solve this task. So this scales really nicely and is pretty fast. In the next step, once we have acquired our training data, we trained a neural model, one that you might be familiar with if you are working in the natural language processing domain. The model is a transformer model called BERT, bidirectional encoder representations. And this is basically a bidirectional masked language model that is pre-trained on lots and lots of data, which is completely independent of the actual task that we want to learn. And because of that, we need to fine-tune the model. And this fine-tuning happens on the training data that we have created in the step or in the previous step, as I just mentioned. And the embeddings, so to say, the representations, the vectors that are used to model the arguments in the BERT model are contextualized, which means that they each individual word is encoded in relation to its surrounding context. And there's one particular task that can be learned, which is very usable for our problem. It is a text pair representation task. that basically models two spans of text or two sentences together. And what we do is we don't model two sentences, but we actually model the topic, which is a short text snippet, and the sentence together, so that they will be encoded in relation to each other, such that our model will actually learn the relationship, not just of the sentence, whether the sentence constitutes an argument, but also whether the sentence in relation to the topic is an argument or not. Here are the results of this process in terms of the outcome that we performed in the evaluation. So on the data that I've just presented, we trained different models. One was trained on only 8 topics, or to be exact, it was trained on 7 topics and tested on the held out topic. And that results in a performance of around 63 macro F1 score, which is okay, but not really good enough to be applied in practice. However, if we train on 40 topics, or again, to be exact, on 39 topics and test on the held out 40th topic, then the F1 score is already above 75, which is pretty good and also pretty close to human performance, which is measured in terms of the agreement between two or more humans. So here we see that this 3-class problem, distinguishing between pro, con, and non-arguments, can be solved by this algorithm with almost human accuracy. Okay, next, let's turn to argument clustering. So grouping arguments into groups of similar arguments. What makes two arguments or sentential arguments actually similar? Let's have a look at the example here. We have 3 arguments about the topic of self-driving cars. Autonomous cars could prove to be beneficial in terms of reducing congestion, and the second one, self-driving cars, would help to minimize traffic jams. Now, these two are obviously somewhat related. They both discuss how self-driving cars could help to minimize traffic jams, whereas the third one, it is expected that self-driving car would reduce car crash by 90%. That is also a pro argument for self-driving cars, but it discusses a different aspect, namely reducing car crash rather than reducing traffic jams. So the argument 1 and 2 are obviously somewhat more related or more similar than the third one to the others. We again solved this as a crowdsourcing task, in which the task was for a pair of arguments, A and B, to label it as being of little or no similarity, some similarity, and high similarity. And we did this with a collection of pre-classified arguments from a given data set. And we also used a sampling strategy with weak supervision based on previous work to make sure that the amount of related arguments in our collection of argument pairs is actually high enough. The resulting corpus is called the aspect argument similarity corpus, which contains of 3,600 arguments on 28 topics, as I said, on a discrete scale, so no, some, or high similarity. And again, it was annotated using crowdsourcing. For the machine learning, we again used the transformer model BERT. Now here, we don't really integrate the topic anymore, but we actually do use the 2 arguments that have to be compared as the 2 sentences in this task, so that the first and the second argument will be encoded together, and then we determine their similarity. We didn't do this with 3 classes, but only with 2, so the outcome is basically a binary label, similar or dissimilar. Now, we didn't only want to label argument pairs, but we wanted to create a clustering from it. So this step has to be performed as well. And for that, we used agglomerative hierarchical clustering to create groups of arguments in the end. For that, you have to specify a pairwise similarity metric, and this pairwise similarity metric is basically determined by the model that I've just been showing on the previous slide, which can detect whether two arguments are similar or not. The number of clusters in the end is not explicitly controlled, but only implicitly determined by a stopping threshold that needs to be set beforehand, and that determines up to which similarity pairs of clusters or groups of clusters will be merged. In our evaluation, we tested both unsupervised embeddings, which means that, or an unsupervised approach, which means that we used pre-trained embeddings that were trained, so they are in a certain sense supervised, but not on the actual task of determining similarity. So they had some other notion of similarity potentially. And supervised means that we actually use the aspect data set to fine-tune this similarity function to be able to calculate a dedicated argument similarity score. Here are the numbers. You can see that in the the lowermost two columns, that is our model using the supervised methods, again in a cross-topic fashion, which means that we test on topics that haven't been seen during training. So this is a quite realistic, or basically the score that you would expect when you apply this to unseen data. And in the middle, you see the unsupervised methods, the collection of different and popular sentence embedding methods like fast text or infrasend. And all of these are already in the 60s, so that is not too bad. However, the supervised methods are much better by almost 10 percentage points. And this again is pretty close to human performance, which you can see in the uppermost row. We distinguish between the evaluation without the clustering, so that is only measured on individual pairs of arguments, and a method that is applying the clustering step right behind. And for that, you basically evaluate only on pairs of arguments within the same cluster, whether they should actually be in this cluster or not. And you can see those scores in some cases are even better than our human performance. Now, how could you visualize the outcome of this? The argument clusters that could be created using the approach shown on the previous slide. Here are a few examples on the topic of abortion. The leftmost cluster, one example would be fetuses are incapable of feeling pain when most abortions are performed. So that would probably be a cluster that contains mostly pro arguments on the topic of abortion, whereas in the middle, you can see arguments that are dealing with arguments using a reasoning from Christianity or religion, so mostly con arguments in that case. And the rightmost cluster is dealing with topics that discuss the constitutional rights in the context of abortion, with a focus on the United States of America in that case. And last but not least, let's turn to aspect detection. So remember, once we have groups of arguments, we also want to label them. And for that, we use argument aspects. Here, I'm giving you a short definition. In this example, we would have two arguments. One is costly and one is radioactive waste. And these two aspects both refer to the concept of nuclear reactors, which again implicitly refers to the topic of nuclear energy. So our requirement for this aspects to form argument aspects is that they need to kind of hold the core reason upon which the conclusion or the evidence of the argument is built. and they are not bound to any POS tag. They are not bound to any grammatical function. They do encode they do need to encode the stance towards the topic, but the topic doesn't need to be mentioned explicitly in the argument, as by the way in any of our arguments. How does this actually work in practice? How did we create training data for this? We had to apply a two-staged annotation scheme that involves both experts and crowd workers, because the first step was actually to annotate free span annotations, which is pretty complex. So we had this executed by trained experts that could basically select any span of text in a range of, or in a number of given arguments. And then in the second step, we use the output of the first step to train a ranker, which is trained on these gold labels from experts. And this ranker would then give suggestions to the crowd workers, which could choose from a list. So they didn't have to select or to choose any sequence of words, but they basically had a list of categories, so to say, which they could choose from. Here is the examples. So the first step is basically really selecting a piece from a continuum, whereas in the second step, where we applied the crowdsourcing, people could choose from a drop-down one or multiple aspects. Here are a few examples. We compared this approach and the outcome of this approach for labeling clusters of arguments to a mere frequency-based approach based on TF-IDF. In the first, the uppermost examples, we have arguments. So all of the arguments are on the topic of drones in this case. And in the first one, the label that has been determined by our aspect detection algorithm would be collateral damage, which in that case is pretty good. All of the arguments actually speak around this topic or subtopic of collateral damage, although they don't explicitly mention it, or only one of them explicitly mentions it. And the TF-IDF scoring in that case would give absolutely, which is not really helpful. So what is given in brackets. The second one, which speaks about privacy. Again, privacy is mentioned in that case in all of the arguments. However, the TF-IDF based solution would give surveillance, which is okay, but I think privacy in that case is the better one. And then in the last example, all of the arguments are discussing some aspect, in that case a negative one, namely damage, and in that case the label extraction from both the aspect detection algorithm and the TF-IDF frequency-based approach would give the same score, the same label. Okay, now let's come to the last part of my talk, which is about research and commercial applications. So if you want to use argument text, how can you use it in your own applications? We have two use cases of this technology that we focus upon. The first one is customer feedback analysis, and the second one is innovation mining for innovation departments or technology assessment. I'm going to discuss these two in a bit more depth. But I also want to mention that we have applications for the media industry to extract arguments from news sources in the with applications for journalism, among others. So for customer feedback analysis, the questions that we want to answer using argument text is how to benefit from unstructured customer feedback fast, with the goal to improve my product and to detect what are the weaknesses of my product and why are they actually perceived as weaknesses by my customers. The obvious competitor technology, if you want so, in that case would be sentiment analysis, which probably most of you are familiar with. However, argument mining is dedicated to considering statements that give reasons. So we don't just assess some opinionated statements, but argument mining requires that actual reasons are given, which in that case are much more helpful to discover problematic aspects, which something can be, hopefully done, that this, in that case, product could be improved. As for innovation management, the questions that we are tackling is whether this the given technology is mature enough. In particular, what might be the risks of novel innovation, because in many or for many innovations, it's easy to find the advantages when there's a hype around a new technology, but it's much harder to find the risks. So this would help me to answer questions like, is it worth actually investing in a new technology? And that enables advanced analytics by assessing the advantages and disadvantages in millions of sources, heterogeneous sources, not just a dedicated collection of magazines, say, but we can also look in social media, in news, on company web pages, and so on. And it also allows me to continuously monitor relevant sources when I have a collection of text that spans a longer time period. I can basically reveal the trend by counting the pro and con arguments over time. I've also brought a comparison of different argument search engines, because argument text is not the only one that is out there. So all of the 4 approaches that are shown in this table are basically research prototypes, which can be distinguished in how they treat the argument classification. Argument classification in that case can be offline or online. Offline would mean that the arguments are classified as arguments or non-arguments regardless of the actual search query, so to say. So they are classified beforehand. And online means that they are classified in real time. So, only when the query is known. So this can only happen obviously once a user has specified a search query or the topic. Argument text is online argument classification, because we first search for relevant documents for the query, and then from these documents we extract pro and con arguments. Another project, args.me, is using offline classification, and for that they use dedicated sources that only contain arguments, so that they only need to retrieve the relevant arguments that are already known beforehand. So this is a bit less flexible. There's also the IBM Debater project, which some of you might know, which uses online classification, but they extract arguments only from news articles and Wikipedia, and they also only distinguish between arguments and non-arguments, but don't apply stance detection. Okay, how to use argument text? We have a dashboard that allows you to do argument search. So here is an example for artificial intelligence, what it would look like. In the dashboard, you get a list of pro and con arguments. You can download the arguments. You can expect where they come from, the date, the sources. You can sort them according to different criteria. And yeah, basically this is applicable to any collection of texts. We also have a chart that or a graph that helps you to detect and understand argument trends. So here the query was e-scooters, and you can see a clear spike in terms of positive arguments when several e-scooter companies launched in German cities in roughly summer last year. However, this hype of positive arguments then quickly decreased into a rather negative perception, I would say, and then it kind of stabilized later on. So this is quite helpful to detect trends. I've also mentioned aspects of similar arguments once they have been clustered. This is also possible to explore in the argument text dashboard. What you would get is a module that allows you to set a custom similarity threshold, which controls how similar the arguments in individual clusters would be. You can again download the result of this, and you can just scroll through the groups of arguments using their labels, which have been determined using the aspects. I also want to mention a sister project in which we applied argument text to detect arguments against the coronavirus, which we refer to as ASG, arguments for the social good. So here, this is a screenshot from the web interface, which is also publicly available on the topic of face masks. And you can see different sources, different documents from newspaper articles in that case that have a certain reasoning on this topic, and we visualize the number of pro and con arguments, and you can also scroll through the arguments. You might have wondered about the quality of the resulting arguments. We've also done a small-scale study, in this case, for the ASG interface, where we queried and evaluated a couple of topics that are relevant for the coronavirus pandemic, so economy, face mask, tourism, and so on. And you can see that both for pro and con arguments, the relevance of the arguments, so whether they actually match or fit to the initial search query, is quite high. So almost 80% of the arguments actually are relevant to the search query. And from those, more than 75 or more % of the arguments also are correctly labeled when it comes to stance, so pro or con arguments. Since this process, as I mentioned a few slides before, is completely online, so the whole classification happens in real time, we also assessed the time that was taken to finish the search query. In the left chart, you can see that in relation to the number of documents that is being searched, so that's basically a parameter that can be configured, we determined the number of arguments that have been found in these documents. So for say 35 documents, you have a little bit more than 100 arguments that are found, and the time that would be required for this is a bit more than 8 seconds. So this is the time that a user has to wait until they would see the result of the search query. You can also use the argument text technology with a couple of dedicated APIs that we have available. We have a classify API, which you can apply to your own text collections to find arguments in your own text. We have the search API, and also for clustering and aspect detection, we have dedicated APIs that are pretty simple to use, as you can see in the example on the right. We also have a lot of open source code and data sets available. If you want to apply any of this or all of it in your own research, have a look at the links that are mentioned here, both when it comes to open source projects, for example, on GitHub, or the data sets that I have been mentioning. So a lot of this is available as open source content. And I also want to mention that this is obviously not just my own work, but a lot of researchers have been involved in this project, most of which are mentioned on this slide in alphabetic order. So a lot of thanks to the team that has been involved in this. And now I also want to thank you for your attention, and I'm looking forward to a discussion and to your questions. Thank you.